So welcome to this first webinar of the IMAGINE-B5G results. Here today we have some Open Call 1 projects which will showcase the results that they obtained with the work within the project. So my name is Ana Pereira. I'm from Ubiware and I'm currently the leader of Work Package 6, Communication and Dissemination. And for today's webinar, I will be your moderator. So IMAGINE-B5G, just a little bit of an introduction, is a StreamD project funded within the SNS-JU Horizon Europe projects. We have targeted 7 verticals, and these OC projects, these OC1 projects, will showcase how they have leveraged the 4 facilities of the project, either to perform platform extensions, so helping the facilities grow, or by performing vertical experiments targeting these 7 verticals. So as you can see, the project has 4 facilities, 1 in Norway, 1 in France, 1 in Spain, and 1 in Portugal. And today we will see projects that targeted these facilities either with the verticals or with the platforms, as I mentioned. So this is the brief architecture that IMAGINE-B5G targeted. And we will now, without further ado, start the presentations. These are the projects funded within OC1. And those that you see with the very nice emojis will be the ones presenting. We will start and kick off this meeting with the Norwegian facility. And I will now stop sharing my screen to allow the OC1 partners to share theirs. And we will start with the LeoSed project, which will be presented by Igor. So Igor, go ahead.
Thank you. I hope everyone can see my screen right now. I'll present to you this project, this Open Call 1 project called LeoSed. LeoSed stands for Leveraging Edge Optical Sensing for Emergency Diagnostics. So as you can see from the name itself, we are an eHealth vertical, but before I continue talking about the project, something a bit more about myself. So I'm a senior research engineer at Huawei Munich Research Center. So I'm here from joining from Munich, from the Wireless Technology Laboratory. So I'm working on 5G, 6G activities on this European research level and researching AI for wireless in the same topics. I was the one working on the LeoSed project, and I will now continue with the introduction from what was our main motivation for starting this project. The incentive for starting the LeoSed project is actually, as Europeans, we see statistics about the drops in fertility and the drops in population, especially for non-urbanized areas. Urbanized areas are getting quite a big chunk. It's of people. It's very hard to find a place even to live. But actually, for the rural areas, we are seeing a very drastic decrease in population. Especially, those are the people that work in those essential jobs, such as farmers, which are very hardy workers. And so the whole issue here is that those people that actually need healthcare on the edges of our urbanized infrastructure actually do require and are quite essential. Like, we need to take care of our farmers, and it's quite essential that we provide this care for them. And our goal was to think of a framework that is capable of providing some support in a way which can be sustainable, in a way that we can provide it contact-free, so contactless, and in a remote fashion, so that there is no need for a professional healthcare worker to aid the service. So what did we actually propose in LeoSed? Said that it is what we call optical wireless sensing. Optical meaning that we work in the line of sight, so in the direct sometimes in the visible light, sometimes in infrared. Wireless meaning there are no wires connecting the patient with the sensing device, and from there we try to discover how can we do this. So how can we provide this remote and contactless service to the patients? The concept of this optical sensing for optical sensing of a person's vitals, of a patient's vitals, is not entirely new. It's called photophletismography. It is essentially it means that with using light, you can actually take the measurements of the patient's well-being. So how does it work? What we do is um, we developed the LeoSet framework, which means we want to position some sensors in a facility where the patients would come as in admission or as in monitoring, so long-term monitoring of a critical patient. And what we want to do with those patients is we want to position sensors so that it has to face their face, as shown in the right, and from the forehead you try to do some signal processing that looks at the changes of the color of the skin, and those changes in the colors of the skin are very, very delicate and very difficult to see with the naked eye. But using these using signal processing, we can actually see the flutter of the movement of the blood on the skin, and based on that we can detect the flow of the blood. And with that, we want to detect two parameters about the patient. The first one is the heart rate of the patient, and the second is his oxygen saturation. This is actually quite important if someone is maybe still operational, but it's so if a patient is awake, but it's actually in danger, there is a danger to his life. Maybe his oxygen levels are starting to fall down, his heart rate starts to go up very high or very low, and this is actually very helpful, such as in the COVID pandemic. You don't have anything touching, no one touches, hygiene is preserved, so the whole system works remote, and it can be done contact free from the patients. On the left, you see the architecture that we said we wanted to implement. So you have red, blue, and green. Green is what our hosts in the Imagine Beyond 5G, that being Telenor, provided as infrastructure for us. So they provided us with the base stations for the Beyond 5G base stations and the framework, the core framework to host our modules for sensing, diagnostic, and statistics. What we brought is the scenarios, so the sensing prototypes on the left and the right, one for admission, where you have very short and quick measurements, and monitoring, where you have a continuous measurements of a person's vitals. So what did we finally achieve is this part is what we want to achieve is this automating of measuring the person's vitals without any contact. How did the prototype look? So this is what a patient would see in front of them. This is a touchscreen. The only reason why we use the touchscreen is you have to accept the GDPR that we are going to process. So any volunteer that wanted to test it, instead of sitting down and the device recording constantly, which is not very privacy conserving, we didn't start any process until you touch the screen. So that is the only contact here, which we could automate by using voice controls easily for this project. We stuck with the touchscreen. But the other things that you see, the key components are, we have an optical camera that actually tracks the forehead ideally. We had another infrared camera that is capable of taking the temperature of the patient as well. We have the 5G UE that is hidden here behind the back that's contacting the infrastructure provided by Telenor. We have the light sources that are calibrated to the sensitivity of our camera, so that we can actually extract those very slight differences in the color of the skin. And we have the prototyping laptop that hosts that the whole prototype implementation was on. The laptop itself was not entirely necessary. It was just to be able to perform changes on the run because this is a prototype itself, but actually the entire thing is very lightweight. In the future, we would actually want to have the entire thing embedded inside the the eHealth device being the camera, just the camera itself. And of course, we have the leftover, the platform and the charging equipment for the prototype. So once you start once you agree to yes, the first thing you see is you see your own picture on the bottom right. So you see the optical one and the infrared one. So your likeness and your temperature, and then you can also follow the your parameters on the screen. This is from the monitoring value. So what once you start the experiment, the first thing you see is, okay, my oxygen is fine, and this is my heart pulse. If the heart pulse starts to get above excitement levels, then you get some alarms. No alarms here. I was pretty calm when I took this test, and if it goes below some critical value, such as maybe 50, maybe 45, it says, okay, heart pulse is too low. Usually oxygen levels are okay until they're above 96% saturation. So anything below that might require the attendance of a professional, and anything below 90 is very suspicious to a critical issue with the patient. So why did we actually need 5G? If we want to, and going beyond 5G, so going to 6G, what was the purpose that we wanted to do is we wanted to test what happens when we want to integrate these lightweight module in the camera and send everything at the edge inside the core of the Beyond 5G platform. So we had the prototype here collecting all the information, so all the video information, which is actually considering the high refresh rate we had to operate in, was very quite a lot of information. So we created a dynamic algorithm that sends all this through the 5G NR implementation, the iCore implementation by Telenor, and the backend that they implemented, so that we can get this at the host, which the host was directly connected at the iCore backend. And this was on the left. You can see the iCore backend, the backend of the Leoset, doing the what any good server does is does the heavyweight processing, while the one on the right only collects, transmits, and shows the information back to the patient. So what was the outcome of the project? The outcome of the project was we did test, of course, the KVIs and the KPIs. The KVIs was mostly just to check whether the application scenario has any utility. So what are we actually aiming for here? We did some market research, we did some due diligence, and of course we did the prototyping, and tried to estimate what would be the societal benefit of implementing Leoset. In general, we estimated that we looked through the literature and checked that usually it takes 3 to 6 minutes of professional time to measure the key values, the key vitals upon each first admission of a patient. So this is the admission. A person, you go to the ER, the first thing they do is check your pulse, check your blood pressure, check your O2, and then you go in the waiting room. If you don't pass that test, you have to go you're assigned a red priority. So and a doctor has to be with you like immediately. And in that case, if we in Germany alone, there's like 98,000 clinics. And if you, okay, this is a bit maybe extravagant, but if we put this for every measurement of vitals, we're going to say in Germany, we're going to save up to 1.2 years of nurse effort in a single day. It sounds promising. And the reduction of personnel time is also the same personnel can be allocated to another jobs. The current prototype we implemented, okay, it was not very cheap. It was around 1,500 euro, but actually we are very well aware that we can reduce. This is still a very big bulky prototype, that we can reduce it to very much lower values, around 200-300 euros, and the OPEX being the server in the background operating all the time, you can cost around 100 to 200 euros per annum. So we see strong potential, but the whole thing is, does the whole system work? So here's where our KPIs actually come into effect. So what do we care? Of course, we care about the accuracy of the system. How well do we measure the the heart pulse and the O2 saturation, but also how fast it operates. Latency is key here, especially because we send high frequency information, so high resolution information to the server. And we actually, with the iCora implementation at Telenor, we saw that latency, we expected something very bad considering the high load of information. So 100 milliseconds, we achieved 13.8 milliseconds on average. Jitter was very low and the connection was extremely consistent from the indoor nodes that they implemented, and throughput was well beyond what we needed. So we actually expected that we're going to need around 15 megabits per second. We actually utilized around 18, while the capacity for the local node was way beyond. It was around 180 megabits per second. It was extremely well.
Igor,
yes.
Please wrap up.
Yes. Okay. And
Thank
so
you.
to wrap up, actually, we did see a 5 beats per second heartbeat error rate and 1% of O2 saturation error rate, which is pretty consistent and okay to measure these values. We did present the information at the LEOSA demo. There was a showcase within Telenor facility, which went incredibly well. And that is it from me. Thank you, and thank you for listening.
Thank you so much, Igor. And we will move forward to the second presentation. I'm going to ask all speakers to please keep in mind that we have 7 minutes per presentation. So now we will have Georges presenting AI for FS.
Hello, everyone. Can you see my screen?
Yes, we can see it.
Okay, perfect. So, good morning. I'm George Lachodimitriopoulos from Local AI, and today I will present AI for FS, Artificial Intelligence for Forest Surveillance, a project we developed under the IMAGINE-B5G Open Call, and our team consists of iLink and Local AI. So, our consortium brings together complementary expertise. iLink contributes 20 years of experience in fleet management, IoT sensors, and European research projects, while Local AI adds deep knowledge in AI and geospatial analytics with a mission to promote sustainability throughout artificial intelligence. Together, we have created an end-to-end forest monitoring solution. So, we are also, Local AI is also partner of the city of Kalamata in the Net Zero Cities mission. So AI for FS is a comprehensive forest surveillance system that combines aerial and ground monitoring. We use drones equipped with multispectral cameras for aerial surveillance, ground IoT sensors for real-time environmental metrics, and edge computing powered by 5G for immediate data processing and response. Here is our technical architecture. The system integrates a DJI Mavic 3 multispectral drone, streaming video via 5G to our edge server. Ground sensors connected through Raspberry Pi devices with 5G HUD modules collect temperature, humidity, and pH data. All data flows through the 5G network to our edge server for AI processing and storage. So we have implemented AI models for forest health monitoring. Our system performs image segmentation and to analyze forest density and calculate NDVI, which is a key indicator of vegetation health. We also use object detection to identify individual trees for forest thinning process. The multispectral camera captures red and near-infrared bands essential for the NDVI calculation. So high NDVI calculated values indicate healthy vegetation, while low values suggest stress or disease. For forest management, we use a powerful AI model based on the RetinaNet architecture to detect tree tops and count trees. This helps actually identifying areas in the forest that require the thinning process. And we also use the Label Studio to annotate new data and fine-tune the model. So for the fire and smoke detection, we tested both YOLO version 5 and FastRCNN architectures, and we selected the FastRCNN based on superior accuracy and better specificity and sensitivity scores. This enables real-time threat detection with immediate SMS alerts to the authorities. Without geospatial analytics capabilities using 5G SA, we were able to generate in real-time maps based on the drone footage. This includes AI model inferencing and affinity projection for raster map creation. The AI for FS portal provides a unified interface for all monitoring data, combining drone imagery with ground sensor metrics in an intuitive map-based visualization. Users access the system through a secure login interface with a modern, intuitive design. The map displays all IoT devices with real-time metrics, including device ID, temperature, humidity, and pressure readings. Also, the portal supports real-time and historical data stored for each device registered in the platform, while an alerting system is responsible for notifying the admin user if any alert patterns are observed in the metrics. So here you can see the first test that we did in a Greek forest near Athens, in Sigrou forest, where we validated our NDVI calculations and tree detection algorithms in a classic Mediterranean pine forest. And we also did a second test in Parnitha Mountain, where we tested the system in higher altitudes, confirming our model work across different forest terrains. We then moved in Norway, and we successfully deployed at Fornebu and Lommedalen area, demonstrating real-time 5G streaming and edge processing capabilities. And the Yaren trial tested our system's mobile deployment capabilities with the team operating from a mobile command center. So I will skip this information about the NDVI. And so our project succeeded through collaboration between iLink's IoT expertise and local AI's geospatial analytics and AI capabilities. Contact information is provided for further discussions. And for the next steps, we plan to apply these prototypes in new use cases in collaboration with the city of Kalamata, one of the net zero cities. We are actively seeking participation in new proposals that focus on smart and sustainable cities, as well as sustainable farming. My email is at the chart in case you need to contact us for further information. Thank you all for your participation and attention.
Thank you so much, George, for your presentation. And without further ado, we will now move forward to 5G Neptune's presentation, for which we have Nicola. Go
Absolutely.
ahead, Nicola.
Good morning,
Thank
everyone.
you.
Thank you, Anna. So here we are. My name is Nicola Di Pietro. I think you can see my slides, right? Already on full screen mode.
Yes, go ahead.
Okay. I'm going to talk to you today about the 5G Neptune project. The name stands for 5G and Beyond Network Extensions towards Public Network Integrated Non-Public Networks. This is a platform extension of the Norwegian facility, and I work for Hewlett-Packard Enterprise Italy. The goals of the project, its targets are summarized here. They are basically threefold. First of all, the idea was to extend the Norwegian facility. In what direction? Towards non-public networks, NPNs in standard terminology, and then to validate the extension through actual vertical experiments. And per se, the extension consisted of the installation of an IP multimedia subsystem, IMS. It's a 5G component on one of the network on wheels available already in the Norwegian facility. also to upgrade the 5G core network of such network on wheels to a newer version, and then to install another instance of a 5G core with IMS at Telenor's premises, still in the facility, dedicated to non-public network experimentation. And then finally, but I would say most importantly, to interconnect the two instances, central site of Telenor and edge site of the network on wheels, into a single public network integrated network on wheels, PNI now, as we called it in the project. The motivation behind the project is summarized here. First of all, we wanted to adopt the perspective of a mobile network operator, such as Telenor, that offers private services over dedicated resources carved out of a public infrastructure. We wanted to test and validate the operation of the network on wheels, so of a moving standalone 5G network, which is autonomous per se, contains all the equipment and components that a 5G network needs, and it is also operational when it is not part of a bigger infrastructure. But we wanted also to see how to integrate these with the public facility, the public infrastructure. So we want globally part of the main infrastructure to be dedicated to private services, to be linked to the main infrastructure when some backhauling is available, but also to have it as an independent edge facility. Also, we wanted to play with the capability of users to access different data networks in the system. And especially we wanted authorized users to have seamless access to the whole network and all data networks in the network, accessible through the networks if you want, but also to have data network restriction for privileged users, authorized users that can access specific resources, for example, for the PDR use case. And indeed, this kind of solution of end-to-end system is applicable to different vertical sectors. I put 4 here in the slide. Let me highlight PPDR, because that's one for which we carried out experiments, and also smart forestry, the Yaren test that was presented before by AI4FS used the network on wheels. A high-level view of the deployed system and then its architecture. All the blocks with a purple color were provided and deployed by HPE. I mean, the rectangular blocks, the radio, the GNOTBs were already part of the facility. So as you can see, we basically have 2 full deployment of 5G systems at the 2 sites. And then we have some wireless backhauling, in this case, between the 2 sites. In this case, it was implemented via the commercial Telenor network. But anyway, it could be any kind of transport network per se. And we configured the components. I can't go into all the details, but we configured the cross-site components to be able to handle traffic and to steer the user plane traffic to reach the specific UPF needed to access either the central data network, typically the internet, or the local data network, where, for instance, we installed mission-critical services and an application for PPDR use case. We validated this architecture through extensive experiments. We defined 18 functional test cases, 4 on-site, over 4 on-site and cross-site scenarios, by combining different traffic possibilities and considering 2 different user profiles, as I mentioned, a general profile that accesses the central data network, and that's it, or a privileged profile for users that also can access the local data network independently from their geographical position. And we tested the core and run integration, the end-to-end connectivity, access to services, access to a specific data network, and even voice over new radio at the edge site, and the possibility of an application to leverage the exposed N5 interface of the core for quality of service control, and also a specific system to synchronize provision data over the two sites. In doing this, we also evaluated certain functional KPIs not related to an application, and we evaluated the uplink and downlink data rate and the round trip time for TCP traffic. I've put some graphs here. The whole list will be available in the final deliverable of the project. Results anyway were highly satisfactory. For example, we had 700 megabit per second data rate in downlink at the edge site. And let me conclude by saying that we also carried out, actually our stakeholders in the project carried out vertical experiments They were carried out in this case by the Norwegian Defense Material Agency and the Norwegian IT Police Department. They experimented extensively with, as I said, an MCX and mission critical push to talk application. They tried to use as many users as possible. They had 55 at hand last year, and they are carrying out these very days some even richer experiments in this sense. They quantified the required data rate for mission critical push to talk sessions. And also with these experiments, we contributed to the KVIs listed here, especially the first responders efficiency and their operational efficiency in areas that are remote and partially covered or out of coverage from the typical public mobile network, and so on and so forth. I see my time is running out, so I'm just gonna thank you very much for your attention, and I'll leave the next speaker.
Thank you, Nicola. Thank you so much.
Thanks.
This concludes the presentations from the Norwegian facility, and we will now move forward to the Spanish facility. And I would like to introduce the presentation for the project Democrats, for which we have Balaz. Please go ahead.
Yeah. Thank you. Good morning.
Sorry.
Sorry.
Yes, go ahead.
Okay, I'm trying to share my presentation. Just a sec.
Okay.
Is it okay now?
Yes, go ahead.
Okay. Okay, it's working now. Great. Okay, hi everyone. I'm Balázs Sonkoly from TKI, from the Hungarian Research Network. And I will present our project named Edge Platform for Dynamic XR Applications, the Democrats. And special thanks to our patrons at UPV, to David, Adrian, Ivan, and Aaron. Let me briefly summarize our motivation and the use case what we addressed in this project. We have recently proposed a multi-user edge cloud-based extended reality platform which supports low latency immersive interaction, remote rendered virtual objects, and we were able to incorporate some latency hiding algorithms in the control loops. So we have very special collaborating operational loops which have very different latency and bandwidth requirements and characteristics. We have a distributed software stack which should be deployed and operated over a distributed 5G or 6G infrastructure. So the main question here is that can we achieve an acceptable user experience with these quite complicated components? And we try to answer this question via the IMAGINE-B5G Open Call experiment. And we could deploy or prototype to a beyond 5G testbed environment and at UPV. So I will not dive deeply into the technical details, just a short introduction of our platform. I don't know if you can see my cursor, but I will try to show some parts of this figure. So we have multiple components. Okay, great. We have a distributed software stack, some components running on top of a head-mounted display. In our case, it was a HoloLens 2 device, so some components are running here. In addition, we have a dedicated device for object tracking and object detection. So it's about the understanding of the environment, which is required in case of mixed reality applications. And on the other side, we have the cloud or edge cloud components. So some parts of the software stack is offloaded to the cloud or edge cloud environment. And in between, we have the network, which will connect the components. And at the lower part, we have the components which are responsible for the object detection and tracking parts. On top of that, we have the components which are responsible for the simulation of the virtual environment and the combination of the virtual and the physical world. So we create the digital twins of the physical objects, and we can simulate the interaction among the physical and the virtual world via these components. And at the top, we have the rendering part, where we create the frame-by-frame video streams, which is sent to the head-mounted devices. Okay, and at UPV, we were able to deploy this extended reality platform to a beyond 5G environment. So we could map the components to dedicated elements in the infrastructure, and we were able to conduct different experiments under different network scenarios: idle network, congested network, and so on. And we also implemented a demo application, which is a game in our case. It's a car soccer game. Especially, it's the extended reality version of the famous Rocket League application. So here you can see that we have physical objects, physical toy car, which can interact with virtual elements, virtual balls in this case, or other virtual cars, and we can play this soccer game with these components. So that's the main message of mixed reality. We want to support the interaction between the physical and the virtual world, and it's a very, very latency sensitive use case. Of course, we can go further. We can add more immersive components to the game. We can add monsters as goalkeepers, for example. It's up to our fantasy how we can extend this game. And as you can see, we support this continuous interaction, this low latency immersive interaction between the physical and the virtual elements. I'm sorry, hopefully it will go to the next slide. Okay. So we have conducted several experiments and we analyzed different components of this architecture. I will not show all the details, but it was important that the loop containing the rendering part, so the object tracking, detection, 3D simulation, and the rendering loop, that was the most important one because it had the most significant impact on the user experience. So we focused on this loop, and we analyzed all the components, how they add their latency to the overall operation. And of course, the most important part here is the networking part, how we can connect the communicating elements. So it's a very, very significant impact on the user experience, and we can have some mitigation options here. So we can mitigate this issue at the application level by introducing jitter buffers. And of course, we have additional options at the network level. We can add priority to given slices. For example, the slice which contains the HoloLens 2 devices. So we have conducted several experiments, analyzed the latency characteristics, especially on latency characteristics of the image downstream, which is the rendering downstream. And if the network was idle, there wasn't any surprise. We have quite low average latency with a very, very low jitter. But when we added the background traffic, of course, the average latency was increased a bit. But the main problem was the very, very large jitter that was introduced. And here we have the time series representation of this measurement, and we can see that we have very, very large spikes in the operation loop, and it has an impact on the user experience. But if we use slice prioritization, we can reduce this jitter, and we can achieve a very, very similar operation point when we have in the idle case. So if we analyze the frame drop rate, which has a direct impact on the user experience, then we can see that we can reduce the drop rate if we increase the jitter buffer size. So that's an option, but at the cost of additional delay. But on the other hand, we can mitigate the problem by slice prioritization, and in this case, we can operate the platform with smaller jitter buffer sizes, but using slice prioritization. And besides that, we were able to reduce the rate of consecutive losses, which was a very, very significant input to the user experience. So this means glitches in the playback of the streams. Okay, and we were able to reduce the multiple the consecutive frame drops in this case. So to sum up, our results show that the latency and jitter characteristics can be managed by prioritizing network slices, including the XR devices. And this is, if we combine it with dynamic jitter buffer approaches. And we have recently presented these results at the ACM Multimedia Systems Conference. And thanks for your attention.
Thank you so much for the presentation. We will now move forward to the BNetTalk project, where we will have Pere presenting the project.
Okay, can you see?
We only see your, not the presentation. Now we don't see anything. We were only seeing your screen, save screen from the computer.
Okay, it's then to share it's using the window.
Mm-hmm.
Okay.
Yes.
Okay, now?
Not on a full screen mode, but we can see the presentation. Just go to the first slide and place it on the full screen, please. I will.
Okay.
Yeah, perfect.
Okay.
Thank you. Go ahead.
Okay. So our our project was a bidirectional education system based on holographic cabins through 5G networks. So just to resume what we did it is we will try validate the use of holographic cabins. No, holographic cabins is something like that, which is a big cabin of more than 2 meters in the educational field using 5G networks for unidirectional and bidirectional content transmission. So it means that we have a first scenario with there is a capture, transmission, and visualization, but this is only unidirectional. And then the bidirectional scenario is in which there is one, let's say, teacher who explains to the lesson to the audience, and at the same time, the teacher can see the reaction or the objects that the audience are showing using this kind of holographic cabins. The main objectives was, first of all, to enhance remote education experience, right? If the system has a better way to provide better education to the current systems of video conference or another ones, achieve real-time interaction. This is a key point, because if there is no real-time interaction, then the experience is completely lost. So we need also to have a human scale representation. So it has to be at the scale level. So the people has to be as height as they are. So it means that you cannot do it the same thing using a small screen, and validate the 5G networks for real-time holography. And to do that, we need to find the ideal parameters for resolution from frame rate, from bit rate, and different type of codecs needed to be employed on holography. And also one of the important things is to achieve latency levels in the level of 100 milliseconds, because if not, probably there will be a delay from one end to the other one, so the experience will be not good enough. And finally, evaluate the impact of holography on education. In the case of evaluate the holographic cabins with versus traditional video conferencing like Teams, Zoom, or another one, We have participants. The participants for these experiments were mainly the students and researchers of UPV facility. We did testing for bidirectional and unidirectional holography versus video conferencing. The evaluation is the knowledge retention questionnaires that we send to the students and researchers. And the content for this was 4 education modules across all methods, 2 for directional and 2 for unidirectional. And finally, the technical setup was the capture site on which there is a full body recording with high-end cameras and audio, the network, which is provided by the facility in Valencia. And finally, the display was these specialized holographic cabins for immersive visualization. And the expected impact of the project was validate beyond 5G network for immersive education and demonstrate holographic technology advantages over traditional remote learning methods. This is the main goal of the. In terms of KPA, there is some technical KPAs where it's the latency end-to-end, which should be around 100 milliseconds. The jitter end-to-end was one of the things that has to be measured in the project, which was the ideal applicable bit rate, which is 20 Mbps, and ideal application settings like image resolution, image frame rate, holography and audio bit rate, video and audio codecs, CBR versus VBR. So there is a lot of different parameters and variables that has to be studied before to put the equipment on the facility to try to find the best results using all of these parameters. And the network throughput is also 20 Mbps from capture and setup. And latency and jitter should be measured in the experiment. The cell bandwidth was 100 megahertz, and the network packet loss we expected to have less than 1%. So in terms of KBA, there is 2 main areas. One is the innovation. The end-to-end bidirectional holograms through 5G network increase the portfolio of solutions of many sectors, not only education, but also training, health, manufacturing, design, retail, aerospace. All of these could be used using this kind of equipment. And also demonstrate the potential training on education. At last, 50% of users give positive feedback on all innovation-related questions. On questions rated from 1 to 5, at least a mean score of 3. In terms of quality education, development of 5G solutions, tools, and applications that improve the quality of experience on remote education. So it means that we want to increase the quality of education through this experiment. 30% improvement over video conferencing education, this is the goal. And several questions on the experiments were made on the QoE survey using a Kagan-Sorriba et al. Method, which is two-factor ANOVA analysis in order to find a way to measure all of these things. The onboarding on the target facility, well, the feature in 3 GPP technologies was network slicing was used. There's the effect of unprioritized traffic versus prioritized. And also B5G applications, Internet of Senses, this platform extension has enabled the UPV to capture and display the holographic content. this system supports the holographic content transmission on this PE, and UPV has provided its 5G network. So let's go on the design of the PE. The design of PE consists on the unidirectional transmission consists of one area of capture, another area of transmission, and of course another area of visualization. This part of transmission is the part of 5G network provided by the network on UPV, and the other ones was all the systems that are needed to make this experience possible. This is the design of the P capture. In the area of capture, of course, you need a camera to capture the person. You need also audio to communicate with them. You need to send all of this to a media server using vMix software, and also after the vMix software, the signal through Ethernet is sent to the 5G network. In the reception area, we receive the data who came from the capture, and also we send to another vMix media server in order to send the data directly to the cabin. So this is the way that we can send the image of a person who is in the area of capture to the holographic cabin. Well, this, as you can see, this is a small brochure explaining that the experiment was done, and they asked for people to participate in it, and the whole experiment was finalized at the end of March using the bidirectional system working, and you can see here some of the images. This is the capture set. You can see a kind of chroma set using also these screens for seeing the return, the camera, and all the computers to work with. And what you can see here is the holographic cabin. In the other side, you can see for one side the teacher who is explaining a lesson, and in the other side you can see here all the audience who is listening him, and is also interacting him in real time. This is part also of the bidirectional. As you can see here, this is the part of what the teacher see the audience, and in the past is the audience who see the teacher. So this is the bidirectional experiment. And all of these are auxiliary elements that we need to monitor what's going on in one of each parts. And now I will pass this part of results to Adrian, who will...
Yes, let me quickly chime in and summarize very quickly the results that we got. Thank you, Pere. So basically, as Pere said, we measured some KPIs, and also we wanted to measure some KPIs. We had some, let's say, goals regarding KPIs and KPIs, and this is a table that summarizes what results we got. So in terms of network throughput, we achieved a base level that was good enough for the audio and video quality for the holographic cabin. So in that regard, we achieved that. We got a baseline level, although we could in the future test with other networks or UE devices to better
to better the quality of the image and the audio, but it was good enough for our use case. In terms of end-to-end latency, we didn't get our goal, but this target number at the beginning of the project was set too low because we proved that a latency of about 600 milliseconds end-to-end was good enough for this kind of application, for educational applications. And we validated that via our quality of experience surveys, and they showed that the lessons could be easily followed, even though the end-to-end latency was a little bit high. In terms of packet loss, we also achieved the less than 1% packet lost in this scenario. The end-to-end jitter was not defined at the beginning of the project, but we also got at least an acceptable level in terms of quality of experience. And in the case of KPIs, the innovation KPIs we achieved, and almost all questions related to the innovation KPI were scored above 3 out of 5, and more than 50% of the users answering positively. And regarding quality education, sadly, it could not be determined because the number of participants in these experiments was about 12, and that is too low to extract any meaningful statistical information. So we, in the end, did an exploratory, more like an exploratory experiment instead of this variance analysis and so on to check if, let's say, immersive applications like this, these holographic displays, are better or not than traditional video conferencing applications. So that is one of the future work that we want to propose to test with more students. Please, Pere, go to the next slide, and this is the final slide, we promise. Yeah, as I said, basically, in future work, we want to test with more subjects to really see if holographic displays are better for education. People on the surveys did answer that they thought holographic communication were better for education, but we could not check it with real numbers, let's say. We also wanted to assess the effect of network slicing in holographic communications because we couldn't do that on this project. We also want to perform this kind of experiments in more classroom scenarios. And most importantly, we want to link this quality of experience versus quality of service. So how KPIs directly affect quality of experience. Yeah, basically this is the end of the presentation. And thank you, Pere, and everyone for listening to us.
Thank you both, Pere and Adrian. This concludes the presentations from the Spanish facility. We will now move forward to the Portuguese facility. I will remind the speakers once again to please try to keep it under 7 minutes. And now we will move forward to Safer Flow, where we have José Guimarães presenting. José, go ahead.
Hello, everyone. Just to share my screen. Can you see my screen?
Yes, go ahead. Thank you so much.
Okay. So, hi, everyone. My name is José Guimarães, and I'm part of the team from OneSource. And today I will present an overview of the Safer Flow. Just to give some context, the floods are becoming a serious problem in many cities. Just last year, we saw the Valencia flood that caused serious damage. So the Safer Flow, with the use of drones and IoT sensors combined with the 5G communication, is trying to improve the decision making and help the first responders. In the Safer Flow, we conduct 2 field trials, one for validation of all the components, and a final showcase with the civil protection, just to give us some feedback. Here we see the water sensors that we developed, and the 5G body kits all the collected data from the water sensors was sent to a command and control center to make it easier for the stakeholders to see the data. And the 5G body kits are equipped with cameras and environmental sensors and biosensors. And also this data collected is sending to the command and control center. We also have drones that are sending video to the command control center. And we also, with the drones, can draw an area, and with the collected image and videos, we can create a 3D map that we can see here. And we also have an AR application to see the video and all the telemetry collected from the drone. This is the command control center that we can see all the data coming from the IoT devices. Here we can see the location from some first responders like firefighters or something else. And this in the right image, we can see the values from the water level sensors. So this is some image from the field trials. In the first one, we put the water level sensors in a bridge, and we try to check the distance from the sensors to the water, and we can see if the water is rising or not. And in the final showcase, we present the safer flow for the civil protection, and we collect some feedback from them. I have a quick video presenting all these technologies from the safer flow. So this is the water sensors placed in a bridge. This is a better image. The trials are conducted in eHealth. So this was a really quick presentation, but thank you.
Thank you, José. Thank you so much.
You.
We will now move forward to the second presentation, DCA with Pedro.
Hello. Hello, everyone.
Hello.
Can you see me and my presentation?
Yes, go ahead.
Okay. So I am Pedro Colorejo. I am from Globe, and I'm here to present our project. We had a partner that was IPM, the Instituto Pedro from Coimbra, that was occupied most of the part of the interaction with the 5G network. And load was most of its importance exploring a system, where a drone can a drone that was made from scratch by load and as an autonomous vehicle, exploring his ability to follow a person and track a person and try to find whether if that person can have or not health problems during a walk in the streets or in a park, and if those health problems are detected, to call an emergency team and start sharing images and data with that team that can help them to help the person more quickly when they arrive to the local. So this aim to use this scenario to explore advanced 5G networking features, especially networking slicing and mobile edge computing. Also to corroborate the ability of a system like this, the amount of volume of data and its usefulness in a system like this, and also to promote the use of augmented reality and artificial intelligence using 5G features. So the three main use cases that we used was to track a user along a certain path in the street, then to detect the relevant health event. When that event is detected, the drone would approach the person and start flying around the user and collecting data. And then this data is visualized by an emergency team while it travels to the event place. And when they arrive there, they already have all the information they need to help the patient. So this is the architecture. We use the Instituto de Telecomunicações of Aveiro infrastructure. And we had this drone. We had persons that would have those health incidents using a mobile application and a wearable that would be sending some biological data. And we had the emergency team that would be able to watch everything that was transmitted by the drone and all the data, and mixed with augmented reality to have this perception. So this is just an example of the drone that we built. This is in an autonomous flight. So he is approaching a person. It starts when the person is detected. It stops in front of it and starts transmitting data. So if when the drone reaches the person, if the person is still moving, the drone is able to accelerate and brake and rotate and to be sure that the person is never outside of the camera scope. And we use artificial intelligence methodologies to detect body parts and also to detect injuries, in this case, in particular, to detect blood. This is still in lab, in development environment. So this would be the vision that the medical team will receive when blood is detected, and we are using fake blood. The body part where the blood is located is detected and shown by using augmented reality in the screen. So we have the arm detection, the head, and now the main body. What are the conclusions? So we had the final trial in a park at eHealth with the emergency protection teams, with the mayor and all the political and the relevant people that were able to attend. And what we had shown was this. So this is the mobile application that would show to the medical team that some accident was happening by detecting the blood and showing the body part that was affected. And then also when flying and the blood is detected, start flying around the person. We had to simulate some movements, and this is the drone in an autonomous way flying, follow a person where blood was detected. As in conclusion, all the initial goals of the project were achieved, so we could explore advanced 5G networking features by using the Institute of Telecomunicações facilities to corroborate the ability of using these 5G features in unmanned aerial vehicles, and to promote all the AI and augmented reality technologies that we wanted also to increase. The main KPIs in terms of 5G connection were achieved, mainly the latency, bandwidth, the reliability, also the accuracy of detecting the emergency, the blood, the body parts, and also the KPIs that we have defined in terms of innovation, in terms of promotion of the good health and safety of people, in terms of security, and also in terms of economic growth, were also not measured until final, but with good indicators that all of these were to be achieved when a system like this is to be put in place. In terms of future works, that we are looking for partners that can go ahead with us to evolve this system to detect other kinds of injuries like heart attack, epilepsy, or disorientation of people, and also the resilience of the drone itself, because it's still lacking of some autonomy problems and its area of coverture of action to be increased. So this is all my presentation. Thank you all for attending and hearing.
Hola, thank you. So we have now concluded the Portuguese facility presentations, and we will now move forward to the French facility. So thank you so much, Pedro. And so we will move forward to Process Serve, which will be presented by Farid. Farid, can you please share your presentation? Okay, so it seems there's a small setback. So let's move to F extension by Paulo Marques, please, and we will try to get back to Process Serve afterwards.
Hello, good morning, everyone. I'm going to share my screen. So please confirm that you can see my slide.
Yes, now yes, go ahead.
Okay.
Thank you.
Okay, thank you for having us. My name is Paulo. I'm the founder of All Smart. We are a company with strong expertise on 3GPP, on the open air interface, open source stack. And together with CMSF, a company that is a software house, we have proposed this extension of the French test bed. And I'm going to present the main objectives and results of this extension. In fact, the F extension has three domains. The first one, it was the implementation in open air interface of the 3GPP compliant two-step random access feature to support short data transmission. Extension 2 is to implement open air interface frequency range 2 features that enables the testing of joint communication and sensing algorithms. And finally, extension 3 is the development of a graphical user interface for the open air interface core network functions that allows the deployment, configuration, and terminating core network instances. So this extension will also allow the visualization of different events exposed by the core network. So all these extensions are related with open interface, as you know, is led by Orecom in France. So we are experts in OAI, and with this project we improve the stability and extend open interface code in several dimensions. So starting with extension 1, that is about the implementation of a 3GPP compliant two-step random access in OAI. The motivation is that random access is an essential mechanism used for initial access and connection establishment between a user device and a 5G network. The condition-based random access procedures is a four-step mechanism, and the motivation for the two-step random access is to reduce the latency and control signaling overhead by having a single round-trip cycle between the WE and the G-Node-B, the base station. The use cases that takes advantage of these two-step random access are massive type communications, 5G RedCap, and IoT applications where you have a lot of devices in the cell. So this is the classical four-step random access that has been already implemented by OAI. And what we did, we extend the implementation to the two-step random access. So we have implemented message A and message B, and the code has been merged with the OAI main branch. So you can see here that the implementation was approved by the Open Interface Software Alliance. It was merged on the GitLab, Eurecom, and this is part of the work deployed, developed by Albismart within the project Imagine Beyond 5G. So it was our first extension. So today it's possible to test two-step random access in OAI, thanks to Imagine Beyond 5G project. The second extension is related with open interface in the millimeter wave, so what is called frequency range 2. So we have work in different features to increase the stability of OAI FR2 and also test joint communication and sensing algorithms using this extension. Again, we work on the OAI code. These are examples of approved merge requests on OAI FR2 that significantly improve FR2 G-Node-B stability and performance. So these are the GitLab from Eurecom where we have merged the code, and is today available for the OAI community to test and do experimentation on FR2. So then we test FR2 in the joint communication and sensing use case, where we have connected the open interface implementation on the core network on the G-Node-B that runs in our product, that is the OAI box, together with the USRP and the up and down converters and phase arrays from TMITech operating on the 28 GHz band. We have a vision sensing camera that extracts visual information about the scenario, and in case there is a line of sight blockage prediction between the base station and the user equipment, the beam is switched through the reflector, and then you can avoid the line of sight blockage that is going to cause strong degradation on the user quality of experience. So this is an example where we join vision and millimeter wave communications. We were at Open Interface Workshop at ETSI showcasing this demo. So I'm going to play this video. Okay, so this is an example where we have implemented an XApp that is able to automatically switch the beam in case there is a detection of a line of sight blockage between the FR2 base station and the user equipment. Okay, so you can see also here on the dashboard that in case, so this is the bit rate in downlink, so around 500 megabits per second. And in case there is a blockage, actually the bit rate strongly degrades. There is a strong degradation of the bit rate. But when we implement the beam switching technique, actually the bit rate keeps on the 500 megabits per second. So there is no degradation because actually we are changing the beam and reflecting the beam in the reflector that then reach the W. So we have tested this in RTORECOM and we demonstrate in the open interface workshop. So finally, the the last extension is the user intuitive dashboard for OAI 5G core network. So as you know, open interface is not just about the GNODE-B, has also an open source implementation of the 5G core network. I know that a lot of people use other cores like Open 5GS, but OAI is full open source, the core network. And our goal with this extension is to develop an open source web-based graphical user interface to facilitate the management of the OAI core network. So it's actually an abstraction layer that simplify the deployment, configuration, and termination process of the 5G core network instances. So we are going here also to give you a short video of this graphical user interface developed in the context of 5G, of the Beyond 5G project. So this is the main dashboard that allows users to configure. So you can see here the GNODE-B that is connected, the user equipment, registration, then all the core network functions with the overview. Then you can click, for instance, in the AMF and you get the logs. You can do configuration, the PLN, for instance, the SPI. So this facilitates the access and configuration of the OAI core network that today is not possible. So today we have to use Linux commands. Here we have a web dashboard that allows access to the logs, as you can see in the OAI code, but also to add subscribers, for instance, in the core. So this is a quick overview. Here see the new UDR users has been added. And again, this is an abstraction layer that facilitates the use of the core network and extract the logs and information from the OAI stack and make it available through a web page. Okay, so finally, in terms of dissemination activities, we were at the UCNC last year with a poster and also with a FR2 demo. We were at Open Interface workshop in France where we have present a demo and as an outcome of the IMAGINE-B5G project. And I'm concluding here my presentation. Thank you. If you have any question, I'm happy to answer.
Thank you, Paulo. We will now move forward to the second presentation. Fahid, can you please present Process Serve?
Yes, of course. Hello, good morning, everyone. I hope you hear me well. I'm sorry I have been disconnected right before I start my presentation before. So thank you, Paulo, for taking the. Okay, let me just start my presentation and to share it with you. Okay, not this way. Okay, let me share. Okay, can you please tell me if you can see my presentation?
Yes, we can see. Go ahead.
Okay, you want me to share also the video of the camera, or it's up to you?
If you can, please. Yes.
Okay. So hello everyone. Good morning. Sorry, so once again for missing the spot before. So I'm Farid Benbadis, and I'm from Hopcast Startup, and we have participated to the Imagine Beyond 5G first open call with a project named Proxy Serve, because actually it's about proximity services, and this project is to enabling proximity services and its server-based practical deployment. So let me first introduce why actually we have Hopcast and why we have this technology we are developing here in Hopcast. Actually, we go from the fact that actually today the functioning of the internet is very centralized, and then most of the content comes from the cloud actually. So we have servers which are running in the cloud, and whenever we need the content, actually we are going to get this content from the cloud. And as has said it, Luc Julia, he said that the excessive use of the cloud is an ecological aberration, because actually we can go get the content from very far locations, while the content can be close to our location. So actually what we do actually in Hopcast is that instead of having the scenario on the left on where the same content or the same file, the same video, the same audio file, the same image, whatever you want, the same content is downloaded from the internet as many times as there are users which are requesting this content. We want to go actually to this scenario on the right, where we have only a subset of users that will get the content from the internet, and then the other users will get the content from these first users. So that's actually a scenario which is known from few decades now, which we call, of course, we had ad hoc networks, etc. But with Hopcast, what we offer is to separate the data plane from the control plane, and to have an orchestrator, which is an entity which will be in charge of monitoring actually the distribution of the content and the needs of the users. So actually Hopcast will sit in between users and knows which user is expecting what content, and what content is available at what users' devices. And with this information, Hopcast will be able actually to establish the device-to-device communication at the right time between the right persons, and avoid actually this control plan to be handled by the users or by their devices. So the Proxy Serve project has actually, the description is that of course it targets the first open call. Actually, we are working on the offloading mobile data, cellular mobile data offloading. So the goal is to have this orchestrator that will orchestrate device-to-device communication between user equipments. Our technology for now is based on two different technologies, one in the iOS environment and the other one in the Android environment, and they are not compatible with each other. So on iOS, it's named multi-peer connectivity. It's a device-to-device framework. It's a connectivity framework. And in Google's environment, it's named nearby connections. And both frameworks work mostly the same way, but they are not interoperable with each other. So we hope that in the future, when we will have this proximity services provided with the 5G, and in the future with 6G, we will be able actually to be independent from these technologies provided by Apple and Google, and to be able to use actually standards of 5G and 6G that allow to implement device-to-device communication between the device. But for now, actually, we rely on these two frameworks that allow us actually to show that we have the ability to orchestrate device-to-device communication, and to have this orchestrator placed in the core of the network and not in another cloud, and placed part of the core of the 5G, 6G core network, and very close actually to the end users. So for that, actually, we have offered to run the orchestrator in the edge of the open air interface architecture. So to come back just to this device-to-device communications, they have many possible use cases. Here I list a few of them. So it can be used in emergency situations and for first responders. It can be used in smart transportation. It can be used actually in a health environment if you want to provide connectivity between devices or connectivity between medical services devices and the user devices. It can be used for edge computing. And actually, we are focusing on using it on content distribution to reduce cellular cost and cellular data, and to reduce the paths followed by data to get the content from the content providers to the content consumers. So the example we have implemented in this open call in our work with Euricom and in Open Air Interface was actually to offer a system that delivers courses material to students without relying on the internet connection. So it reduces the cellular cost at the minimum. And for that, actually, we have targeted university students that get content from their university, but they do not want to consume their cellular plan. And they want actually to receive the materials, the videos, the PDFs, the PowerPoints, the books, etc., without having to consume their cellular data. So the scenario we have put in place is that the students are organized into groups. The groups will actually identify that a content which will be dedicated to a group of users or students. Means that actually all the students are expecting this content. We will have one administrator, which is the professor that's responsible of the classes, that will create the courses and create the groups and manage the groups, and then decide which content should be distributed to the students. And we have provided the students with a mobile application that allows to consume this content. And actually, the students will have two options when getting this, when they will start their mobile application. The first option is to use it the regular way, with the classical way, which is get the content from the internet, so get it directly from the cloud. And the second one is to have an option that says, okay, I don't want the content immediately, but I can wait that actually Hubcast provides me with the content without having to connect through my cellular plan. So we have provided the students with this application, and we have put in place the whole system to allow the distribution of the content without relying on cellular data, but by using device-to-device communication. So for this, we have put this high-level integration description that we have put in place. So we have the application that you have on the phones that you can see here, which is an application that will allow the users to connect, the students to connect, and then to access the content. And this application, of course, is connected to the university courses system, from which actually it will receive in a regular way the content. And it also includes an SDK, which is a Hubcast SDK that we have provided them. And this SDK, which is integrated into the app, has two main features. The first one is to be able to establish this device-to-device communication. And the second one is to be connected to the Hubcast orchestrator, which will send to the devices the instructions to put in place device-to-device communication. So this Hubcast orchestrator, which is integrated in the edge of the OAI core network, is integrated into the NWDAF functions, as we will see in the next image here. Actually, you will see it here. So it is integrated. It has a part of this orchestrator is an NWDAF client that will receive localization information about the students, and it's integrated with the actual orchestrator that knows which user has received which content, which user is expecting which content, and then based on this information, the orchestrator will send instructions to this SDK, and then when the SDKs, when two terminals in the same almost in the same area within 100 meters of each other receive the instructions from the orchestrator, then actually they will establish this device-to-device communication, use it to exchange the content. So one of the phones will send the content it has to another phone which is expecting the content, and then we have some monitoring channel that will send the information to the orchestrator, saying that okay, now we have a new phone that has the new content, and then the orchestrator will take into account this information to distribute the content in the future to other students. So this educational content direct sharing, the objective was to deliver the educational content between two devices without relying on the device on a cellular network. It's based on device-to-device communication and proximity-based communication. It's cost efficient because it reduces the data cost by bypassing the traditional data networks and routes. And it allows actually to make access to this educational content more accessible and more inclusive, especially for regions where cellular access is very expensive. And also because actually the routes this content is going to go through are shorter than the usual routes, then actually we leverage these communications to minimize actually the battery usage, because actually using device-to-device communication is less power consumer than using the cellular, the usual cellular data. And actually we make actually this content distribution more sustainable. So about the trial and the pilot we had actually about the orchestrator deployment, actually it has been deployed on the open air interface edge part of the core network. It has been integrated with the NWDAF, the network data analysis function. So it allows us actually to get measurements of some metrics of our deployment and some metrics in real time. And actually, it has actually, we have, of course, verified that user mobility is well received by getting the information from the NWDAF, and that the integration was working properly. From the content sharing part, actually, so we were just creating a group of students. We are distributing a content for the students, and we are, of course, expecting that the device-to-device content is well triggered from the orchestrator, and once it's triggered, it's well received by the users, and then we have measured some KPIs. Here you have some photos of the workshops we had at Euricom with the Euricom team, which I say hello today. Actually, it was a very good collaboration we had with them. They were it was very easy to discuss with them and to achieve our common goals. We have implemented this mobile app that we have shared to some students of the Euricom. They have accepted actually to play the role of students and to see if the content is well distributed, etc. So we thank them too. So this is a feedback on the experience with the facility. I have already said that we had very good technical support. We had very good documentation that helped us to integrate our orchestrator easily in the in OpenAI core network. And here I'm going to the measures we have made. So we have made some measures which are really specific to the Yes.
Please wrap up.
Yes. Okay. So
thank you.
We had, thank you. I won't go through this to the measures. It was so I just stick with that. So we have actually there is one of the KPIs we did not measure, but all the others were above our expectation, as you can see here. I won't go into details. So the work was achieved following the plan. So we had some delay introduced by some difficulties, but we went over that. We had 2 trials there. We have been able actually to do everything, and we have planned, and we have been able actually to show that we could integrate the orchestrator into the core network. And we would like actually to thank actually all the team of Euricom for that. So thank you very much, and sorry for being a little bit long maybe. Thank you.
Thank you so much, Fahid. And now we will proceed to the last presentation. So Wasim presenting the work on the project Camera API.
Okay.
Thank you.
Just one moment, please. Can you see my screen?
Not yet.
Please let me know when.
No, we are not seeing your screen.
Just one moment, please.
Of course.
And now?
No, nothing is being shared yet.
Not yet.
No, if you wish, I can present and you can just let me know when to share, when to change the slides.
Okay. Just let me try another, give it another try.
Okay.
Can you see it now?
Let me confirm. No.
Mm.
Do you wish for me to share the presentation?
Yeah. Just go ahead. Okay.
Okay, just a second so that I can put it on big mode. Okay, can you see it now?
Yes.
Okay, just let me know when to change the slides, okay?
Yeah, of course. So, hello everyone, I am Wasim from Pinglatech. Today I will share with you the work that we have done as part of the IMAGINE-B5G Open Call 1. The project title was Extending the IMAGINE-B5G Framework and Facilities using Camera API. Can you go to next slide, please? So our main goal was to simplify and standardize how developers access advanced 5G and edge features. As the Camera API helps abstract the complexity of 5G core functions by making them accessible and programmable through open interfaces. And just to mention, this work was a collaboration with the Eurocom facility in France. Next slide, please. So even though the 5G core is powerful, but it's often underused due to the complexity of accessing its features, and this slows down innovation. So our motivation was to break that barrier by offering a standardized, open, and secure API layer based on Camera specification. Next slide, please. So here is a high-level look at how our system is structured. Each Camera API runs as a separate microservice and containerized using Docker. All of these APIs are securely connected to the network exposure function, which acts as a gateway to the 5G core. This ensures secure and event-driven access to the network data and capabilities. Also, our architecture supports multiple security layers, including JOT authentication, OAuth2 login, and two-factor authentication using OTP. Can you go to the next slide, please? So we implemented overall 9 Camera APIs, and we grouped them logically into 4 main categories. For network monitoring, we have device identifier, device location, and device status APIs. For performance and control, we implemented traffic influence and quality on demand. Then we have edge intelligence APIs such as edge cloud and connectivity insights. Finally, we have also implemented business-related APIs like carrier billing and site-to-cloud VPN. All of these APIs are fully documented using Swagger, and they can be accessed through Unified Developer Dashboard. Next slide, please. Moreover, every API is exposed through secure Swagger interface and backed by production services. We included strong authentication and access control using token-based security. More importantly, we have enabled subscription and notification mechanism via the NEF. So the external application can subscribe and can subscribe to live events like location changes and the connectivity status and so on, and receive real-time updates based on the subscription, on their subscriptions. Next slide, please. To test the full pipeline, we built use case around the UAV or drone smart routing. In this scenario, UAV subscribes to its own geolocation updates using the device location camera API connected to the NEF. If geofencing violation is predicted or if the UAV approach restricted zone, it gets rerouted in the real time. So this validates not just the API itself, but the entire event drive interaction with the 5G core networks. Next slide, please. So we achieved a lot during this open call, as all 9 camera APIs were successfully implemented. Each one was made available through Swagger interfaces. We also integrated secure access mechanisms, including JOT, two-factor authentication, and OAuth 2 protocol. The NEF subscription model was tested and verified for key APIs like device location. And lastly, we developed a unified dashboard that allows developers to easily explore and interact with all available APIs from one place. Next slide. The biggest impact of our work is that it bridged the gap between advanced 5G features and real-world applications. We made it easier for developers to access sensitive network features in a secure and standardized way. Also, through this project, we enabled vertical use cases like UAV routing, smart routing, and demonstrated the role or camera APIs can play in supporting next generation applications. We also reinforced the IMAGINE-B5G 5G platform by making it more interoperable and programmable. Next slide, please. Can you please play the video? It is video, yeah. You need access.
I don't seem to have access to the video.
Yeah. Can you let me share my screen another
yes,
time?
If you are able to, yes, perfect.
I don't know what happened. It cannot be shared. So it was just demonstrating the video to showcase like our implementation. It was short video. And it was the last slide.
Okay. Thank you so much for your presentation, Wasim. We would like, on behalf of the IMAGINE-B5G project, to thank all the speakers from the OC1 project that agreed to be here in July presenting their work. And we'd also like to thank all the participants that stayed active in the session and learned from all the projects what was achieved. Due to the long hour, I will not open a Q&A session, but feel free to reach out either to the IMAGINE-B5G project or to the open callers to learn more or to ask specific questions you may have. Thank you, everyone. We will share this session on IMAGINE-B5G's YouTube channel, so pay attention to it, like it, share it, and we will come back once again with other open calls and their results. Thank you, everyone.